How you guys doing today? We are on to lecture number 2 about the nervous system. Last time we met, we did a lot of anatomical stuff. We talked about the general categories of the nervous system. We talked about the differences between the nervous and endocrine system. We talked about the two cell types, glia and neurons. And we went over the neuron's anatomy. Now, here we have a typical neuron, and I want to kind of review it with you a little bit before we get going. So we got a typical, beautiful neuron here. Right here is the cell body or the soma of the neuron. This guy right here is the axon, which is already labeled axon for me. The beginning of the axon is the axon hillock. These branches on the axon down here are telodendria, literally branches at the end. The little enlarged regions at the very tip are called synaptic knobs or axon terminals. Axon terminals because they're at the end of the axon. Synaptic knobs because, well, they're kind of knob-like, and they would form a synapse. Remember, a synapse is where two neurons are going to meet and one neuron is going to exchange information with the other. Or a neuron could synapse with like a muscle cell and stimulate it to contract. Now over here we see a lot of dendrites. Remember, dendrites are going to get signaled by other neurons or by sensory cells. And then, yeah, what else do we have here? This neuron, by the way, does not have any myelin sheath. So there are no oligodendrocytes or Schwann cells wrapping around the axon to form that insulating core. And that's okay, not all neurons get that. Now, what I want you to remember is that a neuron would get some information at its dendrite, perhaps. And then that neuron would have to send an electrical signal onward, down its dendrite, down the cell body, to the axon hillock, and then an electrical signal would have to go down the axon, all the way down the axon, down the telodendria. It wouldn't go down just one like I'm depicting here. It would go down all of them. But I'm just going to draw one pathway. And then once the electrical signal got to the axon terminal, what would the axon terminal do? The axon terminal would release lots of signaling chemicals called neurotransmitters, which maybe they would bind to another neuron and stimulating it. Now, the question we're going to answer today is how the stimulus right at the beginning here at the dendrite creates an electrical signal in the dendrite and the soma, and then an electrical signal down the axon, which prompts the release of neurotransmitters from the axon terminal. Because this is how neurons communicate. And neurons communicating is the key thing. Neurons communicating is how we control muscles. It is how we control other organs and tissues. Neurons communicating is how I am talking to you, how you are understanding what I'm saying, how you're nodding your head and you're like, yeah, I get this. When I make jokes, that's neurons communicating. When you laugh hilariously because I'm so funny, that's neurons communicating. All right. So I do want you to notice a couple things here. I made black arrows for my electrical signals in my dendrite and soma, and then green arrows in my axon, because it's actually going to be two different kinds of electrical signals. But they have a commonality. Both of them, all of the electrical signaling in a neuron, depends on a fundamental characteristic of neurons. And that fundamental characteristic of neurons is something called a membrane potential. Neurons have a membrane potential. Neurons have a membrane potential. And that membrane potential, in simple terms, that means there is an electrical difference between the inside of the cell and the outside. So for example, we got this little box here on this axon. Then we're zooming in on it right here. Here's the plasma membrane of the axon right here. And notice on the outside, we have more positive charges. On the inside, we've got more negative charges. So there is an electrical difference, like we just said. And that electrical difference is called a membrane potential. And we can actually measure this using something called a voltmeter. And you stick an electrode inside the cell. The voltmeter tells you the value of this electrical difference, the value of this membrane potential. And it is about negative 70 millivolts. And that negative just means the inside is more negative than the outside. That's all the sign there means. Now, this is a tiny amount of electricity here, a tiny amount of voltage. Think about it for a second. Like, what kind of battery do you have in your smoke detector in your house? You have a smoke detector in your house. Hopefully you do. Go look inside and check out the battery if you don't know. The battery in there is a typical 9-volt battery, which is, the little rectangle guys. A 9-volt battery like that is 9,000 millivolts. All right, you could touch that battery, that 9-volt battery, to your tongue. It won't hurt you. It might tingle a tiny bit, but it's not going to electrocute you at all. And it's 9,000 millivolts. This electrical difference is negative 70 millivolts, so it is very, very small. Okay, so sending electrical signals in my neuron is going to depend on having this situation. And really, really simply, the way it works, really simply here. Let's say I stimulate this dendrite somehow, okay? Right there, boom. I stimulate that dendrite right there. And the stimulation causes the dendrite's membrane potential to change. Whoops, I didn't mean to make an arrow there. Let's put it on my pencil. There we go. So I stimulate my dendrite. The membrane potential changes right here, which makes it change 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 right here. You can kind of see where I'm going with this. It makes it change right here, which then makes it change right here, and change right here, and change right here, and change all the way down. Like a row of dominoes being knocked over, the membrane potential changes in sequence. And when that change finally gets to the end, then at the end, our axon terminal releases neurotransmitters. There's my neurotransmitters right there. Beautiful. So, neurons have to send electrical signals. To do that, they need this membrane potential, which is an electrical difference between the inside and the outside. And the beautiful thing about a neuron is that if I change the electrical signal in one spot, and I got to do it enough, I got to do like a big enough change, but if I change it enough in one spot, it changes in the next spot, and the next spot, and the next spot. And it goes all the way down the neuron. Now, by the way, you might be wondering, like, how far is all the way down? So, think about yourself here, okay? Stretch out your leg, and imagine, like, look at the bottom of your foot, maybe. Imagine the bottom of your foot, okay? You have muscles in the bottom of your foot. The motor neuron controlling the muscles in the bottom of the foot is in your lower back. So your longest neurons are going from your lower back to the bottom of your foot. So depending on how tall you are, that could easily be a meter. It's long though. I mean, you can measure that on yourself and basically have an idea about how long your longest neurons are. And of course, this is why using electrical signals is such a smart way to do it. Because this distance, it's too much for just like plain old diffusion. Even for your blood to carry the signal, it's too much, and that's just too imprecise. So electrical signals are where it's at. All right, What we're going to do now, and I know I spent like 10 minutes on this first slide here. What we're going to do now is figure out why our cells, like what creates this membrane potential. And then also, we're going to figure out figure out how this change actually works. So that's our plan. So let's go ahead and do that. Okay, do you remember this protein here? Tell me you remember this protein. Tell me you do. Even if you don't, just tell me you do. Say, I remember it, just so I'm reassured. This guy right here, he is the sodium potassium pump. Do you remember that guy? The sodium potassium pump? He is going to be one of the things that helps us establish a membrane potential. If you recall, this protein breaks down a molecule of ATP, turns ATP into ADP, so adenosine triphosphate into adenosine diphosphate, plus another little phosphate group. And this releases what? This change here releases what? It releases energy. And we use that energy to move 3 sodiums out of the cell and 2 potassiums in. Check out the electrical imbalance here. I got 3 pluses going out for every 2 pluses going in. So every time this happens, and this protein is always working, every time this happens, we get a little more negative on the inside. And we just said the membrane potential has that value of negative 70 millivolts, where that negative referred to the fact that the inside was more negative than the outside. Okay, fantastic. That's one thing that helps establish a membrane potential. But there's something else. I have some other proteins here. Check out these proteins. What kind of proteins are they? What did you say? Did you say channel proteins? That's awesome. They're channels. Did you say integral proteins? That's perfect. They're integral proteins. Maybe you said transmembrane. That's beautiful as well. But these are proteins that are found throughout your entire neuron. So like in your dendrites, in your soma, and in your axon. And they are called potassium leakage channels because they let potassium leak out. Inside the cell, we have a high potassium concentration. Outside the cell, we have a low potassium concentration. So potassium is always leaking out. And when potassium leaves, look, potassium is a positively charged ion, which you may remember from chemistry class is called a cation. And when that positive charge leaves, it makes the interior more negative. In fact, if we stopped right now, the membrane potential, the electrical difference right now, would have a value of negative 90 millivolts. But what did we say earlier? We didn't say it was negative 90, did we? We said it was negative 70. So something else has to be in play. And the other thing in play is another type of channel protein that is ubiquitous, found everywhere, in our neurons, so in our dendrites, axons, somata, etc. And that is the sodium leak channel. Sodium is high on the outside, high sodium on the outside, and low on the inside. And so sodium is always leaking in. And that is going to make my interior a little more positive, which brings me from negative 90 down to negative 70. And this is my membrane potential. Now, oftentimes, we use the word resting when we describe a membrane potential. And we use this term when the neuron is not doing any signaling, when it is just resting. So the resting membrane potential is negative 70. It is a consequence of the 3 proteins we mentioned earlier, and I have 2 of them here, potassium leak channels, sodium leak channels, and the sodium potassium pump. Okay, remember, this is important. This membrane potential matters because changes in it are going to travel, and those traveling waves of change in its membrane potential is the electrical signal that a neuron uses. All right. Another word to describe this situation. A neuron, which we already established, has a membrane potential, a difference in the electricity on the inside, more negative, than the outside, more positive. The value for that is negative 70 millivolts. In a situation where there is an electrical difference, we say that thing is polarized. So the neuron cell membrane is polarized. Means there is a difference. Politics is very polarized in the United States right now. There's not a lot of agreement. There are a lot of differences. So my neurons are polarized. There is a difference between the inside and the outside, an electrical difference. Okay, let's keep on going. We got a beautiful multipolar neuron here. Beautiful multipolar neuron. It has dendrites. Let's label a few things just because I love to label things with you guys. Dendrites, soma, nice nucleus, nice nissel body. Don't think we mentioned that today. Axon hillock, telodendrion right there. Axon terminal right there. Gorgeous Schwann cells right there. And in between them, the nodes of Ranvier. All right. So, this neuron, we know its job is communication, right? Neurons communicate with each other. Neurons communicate with muscle cells, gland cells, etc. And the communication, this signal, needs to travel from one end to the other. So an electrical signal needs to travel down my dendrite, down my soma, and then down my axon. The electrical signals, they are waves of change. Waves of change in my membrane potential. And I talked about this earlier. The membrane potential changes up here, which makes it change in the next spot, and the next spot, and the next spot, and the next spot, and so on, and so on, and so on, and so on, all the way down. All the way down. The wave of change in the membrane potential goes all the way down. And yes, I'm going to draw these X's all the way because I figured why not? It's too much fun not to. And when we get to the end, what does that axon terminal do? What does it release? Neurotransmitters, which can then signal another neuron or a muscle cell. Now, as this picture depicts, as I mentioned earlier, it is actually a different kind of signal in the dendrites and soma versus the axon. Although both signals are waves of change in the membrane potential. We will see how they are similar and how they differ. Do not worry. Let's get started on that. So we've established that a neuron has a membrane potential. We've established that electrical signals in a neuron are going to be the way the neuron sends a signal. Hold on, I don't even know what I just said. Rewind for 1 second. We've established that changes in the membrane potential are the way the neuron is going to send a signal from one end to the other. Now, when we change the membrane potential, we have some terms for that. And we've got it depicted on a graph here, okay? So I want you to check out the the y-axis of my graph. So here's the label for my y-axis. It says membrane potential, which is measured in millivolts. And notice how we are starting with the membrane potential being negative 70, right? What do we call that membrane potential? We said it was resting, when the neuron's not doing anything. Now my x-axis in this graph here, it doesn't say it, but there is an x-axis. Oh, does it say it? I just covered it up. Yeah, haha. There it is. It's time. So you can see the 3 ways my membrane potential can change. If my membrane potential is at rest, like we are right here, negative 70. We know there's an electrical difference between the inside and the outside, right? And a word we use for that, we said the neuron was polarized. So the neuron is polarized. Now, when we change the resting membrane potential, one of the obvious things we can do is we can make this number, negative 70, get more positive. That's what's happening in the graph right here. The graph is going up, right? So from negative 70 to negative 60 to negative 50 to negative 40, right? That change, when the membrane potential becomes more positive, that change is called depolarization. When you stick that prefix D in front of a word, what does that mean? If you're dehydrated, you are lacking water, right? So if you are depolarizing, you are removing the polarization. We said the neuron was polarized because we said the inside was more negative than the outside, right? There was that difference. But we're removing that difference by making the inside more positive now. So we're making the inside more like the outside, we're making it more positive, and that is called depolarization. Now, if we depolarize, meaning we go more positive away from membrane potential, we can also go from that depolarized state and get more negative again, and we can go back to resting. That return to the resting state is called repolarization. We're making a difference again. Repolarization, again, difference. So if we depolarize, we can then subsequently repolarize. Okay, what else can we do? If we keep on going, we're at rest again here, and now the interior of the neuron is getting more negative. Negative 80, negative 90, negative 100, etc. And that is called hyperpolarization, because we now have even more. Hyper means to a greater degree, right? More. So we have even more of a difference. So these are the three basic ways we can change the membrane potential. And we're going to see all three of these ways when we look at the signaling that neurons are going to do. Okay. I should give you like an extra credit question, right? Why not? So I'm going to give you an extra credit question, okay? I'm going to give you 3. Or should I give you 4? Give you 4 here. I want you to tell me what would happen to the resting membrane potential if there was an influx. I'm going to switch colors here just because I don't really like this light green. If there was an influx of sodium, so sodium ions went into the neuron, what would that do? I'm going to use one of these 3 words. So the neuron is at rest, and there's going to be an influx of sodium. That's question number 1. Okay. Question number 2. What would happen to the membrane potential if there was an efflux? That's just a fancy way to say exit, flowing out. If there was an efflux of potassium, what would happen to the membrane potential if potassium left? So again, we're starting from rest. In each of these situations, we're starting from rest. In the first one, sodium comes in. In the second one, potassium leaves. In the third one, what would happen if there was an ingress of chloride? And ingress just means going in. I'm just using fancy words for going in and going out here. So chloride going in. Okay? Lastly, what would happen if some calcium rushed in? No more fancy words. So in each of these situations, we're starting at rest. What would happen to the membrane potential in each of these situations? So send me your answer in an email, of course. Tell me, say like sodium influx would cause blank, potassium efflux would cause blank, etc. Okay? So write it out for me. Just makes it easier for me. And that is your latest extra credit question. All right. Let's keep on going. And let's talk about how depolarization might occur. So, depolarization is going to be when that membrane potential gets more positive. So we start at rest and it gets more positive. I see a graph of depolarization here. So I started at rest right here. Started at rest right here. Resting, resting, resting. And then we go up, getting more positive. And that change right there is a depolarization. Okay? So from here to here, depolarization. Now, how does it happen? What I want you to notice is this guy right here, okay? This is a synapse. I have a dendrite of one neuron, and there is an axon terminal coming right up against it. An electrical signal is going to travel down this axon to the axon terminal. That electrical signal is going to prompt the, it's going to prompt the release of neurotransmitters from inside the axon terminal to outside of it. They're going to do some exocytosis. And they're going to be in that space between the two neurons. Do you remember what that space was called? That space between the two neurons in a synapse was called the synaptic cleft. Okay. So, those neurotransmitters, when they're released from the axon terminal, they're going to diffuse to our dendrite, and they are going to bind. They're going to bind to these ion channels. These are in the plasma membrane of the dendrite at that synapse. And these ion channels are said to be transmitter gated. If they're gated, that means they have a gate, okay? Which means they can be open or closed. Now, what do you think is going to open these channels? It's the binding of the neurotransmitters. The neurotransmitters bind to these channels, and it causes these channels to open. And when these channels open, look what's happening. These channels are channels for sodium. And sodium is rushing in. Sodium is rushing in. And sodium is a positively charged ion. So, the membrane potential is going to become more positive. In other words, it is going to depolarize. Hey, we just answered one of the extra credit questions, didn't we? Hopefully, you've been paying attention. All right. This is one of the ways we can achieve depolarization. Now, bear in mind, this depolarization, it only happened right here. It didn't happen everywhere in the neuron. It only happened right here. Because that was the only place, as far as we know from this picture, that the neurotransmitter grabbed on to the ion channel. Okay. Let me clear all this mess. I want to draw your attention to the graph down here again. Notice we were starting at rest, -70, then we depolarized, right? Because of that influx of sodium. And there was influx of sodium because the sodium channel opened. And the sodium channel opened because neurotransmitters grabbed onto it. And neurotransmitters grabbed onto it because they were there. They were there because the axon terminal released them. The axon terminal released them because a signal arrived. Okay, all that being said, I want you to notice that they've labeled this depolarization an EPSP. EPSP. EPSP stands for Excitatory Postsynaptic Potential. Now, what does that mean? The word potential refers to the fact that we're changing the membrane potential here, okay? Postsynaptic refers to the fact that the cell we're talking about is the one receiving the signal at our synapse. So notice he's been labeled up here as the postsynaptic dendrite. The axon up here would therefore be known as presynaptic. Excitatory. Why do we use that word excitatory? We used it because this depolarization is going to make it more likely. The depolarization is going to increases the likelihood, let's jump down here, the likelihood that sorry, my words are run together a little bit there, neuron sends its own electrical signal. All right. This kind of change, this depolarization in the dendrite, is no guarantee, but it makes it more likely that this postsynaptic neuron, this neuron receiving the information, being stimulated, is going to send its own electrical signal. May or may not happen, we don't know yet, but we know it became more likely. All right. You guys with me? I hope so. Have you taken a break or two? I hope so. Take like 10 breaks if you need to. It's the beauty of watching the video. You need a break, you take a break. You need to rewind. You watch it twice, you watch it 3 times. Hopefully. I'm actually kind of dismayed sometimes when I look at the statistics on these videos I post. So I can see like how many people watched it. You know, how did they watch the whole thing? Did they only watch like 5 minutes of it? And sometimes it is disappointing to see those statistics. All right, let's talk about hyperpolarization for a second. Okay, I got another synapse here. Let's switch it back to my drawing tool here. Got another synapse right here. Another beautiful synapse, okay? And I have my axon and my presynaptic neuron, my dendrite and my postsynaptic neuron. Now an electrical signal is going to come down this axon, and it is going to cause neurotransmitters, there we go, neurotransmitters inside the axon terminal to be released to undergo exocytosis, and they end up in the synaptic cleft. And then those neurotransmitters, here they are right here. Here's some of them down here. We see them down here. Beautiful. Those neurotransmitters are now binding to a different receptor protein here. This is a different one. Okay? It's a different neurotransmitter too. You notice it was purple instead of green this time? And this channel, this transmitter-gated ion channel, is a chloride channel. It is a chloride channel. And look what chloride does. Chloride is going to rush into the cell. Check out what kind of ion chloride is. Chloride is a negatively charged ion, which we refer to as an anion. And so when chloride rushes in, that makes the interior of the cell at this particular spot more negative. That makes the membrane potential more negative. So we start out at rest and then we got more negative. And what kind of change is that? That is a hyperpolarization, because the inside is now more different. The inside is more negative, more different than the outside. So it got hyperpolarized. So electrical signal came down on this particular axon, who's releasing a different neurotransmitter. It diffuses across the synaptic cleft, binds these new receptors, which are chloride channels. When they open, chloride rushes through, and we hyperpolarize. And this hyperpolarization is referred to as an inhibitory postsynaptic potential. So last time we had an excitatory postsynaptic potential. This was inhibitory because it decreases the likelihood that this neuron that received the signal is going to send a signal of its own. All right. So these are two ways we change the membrane potential. We just talked about how we can do hyperpolarization, and a moment ago, depolarization. We'll hit repolarization soon enough. Don't sweat that, okay? By the way, you notice we just answered another one of those bonus questions? Yay. Okay. Excellent. Excellent. All right, in our earlier two pictures, we had started out with a synapse on a dendrite. So let's say neurotransmitters grabbed on to this dendrite at that place where my lightning bolt is signaling. Let's say that there was a depolarization right here. That depolarization is not going to stay put. That depolarization is going to travel. The depolarization will travel and travel. It'll travel down the dendrite, down the soma, and it'll get to the axon hillock. So, if I depolarize my dendrite, I am probably going to depolarize my axon hillock. Question is, how much depolarization is going to happen at that axon hillock? That axon hillock has a magic number. There is a magic membrane potential. There is a magic membrane potential. So, when neurotransmitters bind right here, and we really could have started anywhere, this is just our example. When neurotransmitters grabbed on right here, they depolarized this spot. That caused a wave of depolarization that traveled all the way to the axon hillock. That makes the axon hillock depolarize. Question is, will the axon hillock depolarize to the magic membrane potential? The magic membrane potential has a name. You might have guessed it already. If you're looking at this slide, you might have guessed it. The magic membrane potential is called the threshold potential. If the depolarization that happens right here is enough to get us to the threshold potential, then an electrical signal will go down the axon all the way to the end. If we reach that magic number, as long as we get to it, doesn't matter how much greater than it we get to it, as long as we get to it, an electrical signal will travel all the way down the axon to the end. Even your longest axon, the one from your lower back to the bottom of your foot. Now, this threshold potential, it does have a value. The value is negative 55 millivolts. So the threshold potential has a value. That value is negative 55 millivolts. So, if we depolarize our dendrite right here. That depolarization travels, bum, 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 and we get to the axon hillock. The axon hillock then depolarizes. And remember, the axon hillock will be at rest at first, so it'll be at negative 70. Question is, will it get to negative 55? If it doesn't get there, like in this example here, guess what happens? Nothing. Nothing happens. The signal dies right here. If it does get to that magic number, then we get an electrical signal that travels all the way down the axon and prompts the release of neurotransmitters. Okay. That magic membrane potential is called the threshold potential, and its value is negative 55. All right. Kind of lost my train of thought there. Had to pause the video for a moment. I think I'm done here. We got to talk now about a couple things. How this signal moves from where the neurotransmitter binds to the axon hillock. Then what happens if we get to that threshold potential? How the signal then continues. That is what we're going to do. Let's go ahead and do it. Now, remember, we said that when we get a depolarization, like we have in this graph right here, from rest, we depolarize. That depolarization is caused by an influx of sodium through an open channel. We don't see it, but there's got to be like a neurotransmitter grabbed on right here. You can see the gates on this channel are open. Sodium rushes in, and we depolarize. Such a depolarization is called an excitatory postsynaptic potential. Why? Because what this is going to do is it is going to cause our axon hillock. Remember the axon hillock? It's going to cause the axon hillock to go towards, and I mean is membrane potential, the membrane potential of the axon hillock. Let's put that in there. Membrane potential of the axon hillock. It's going to go towards the threshold potential, the magic number. And by going towards the threshold potential, we are becoming more likely to get an electrical signal on an axon, and that's why it's called an excitatory postsynaptic potential. Okay. Similarly, if chloride rushes in, we go from rest, and we get more negative 90. We're going towards that. And so what we're doing here is we're going to end up taking our axon hillock away from the threshold potential, making it harder and less likely to get there. So making our neuron less likely to send an electrical signal, and that is why we are using the word inhibitory here. All right, excellent. So, we know we have electrical signals in our dendrites and soma. So they would start wherever neurotransmitters are binding. So let's say it started right up here at the beginning of my arrow. Then those signals would travel down the dendrite, down the cell body, to the axon hillock. Those traveling waves of change, whether they're depolarization or hyperpolarization, either way, those waves of change traveling through dendrites and the soma are called graded potentials. And an analogy is throwing a rock into a body of water, giant body of water right here. You throw a rock in, it makes waves, those waves travel. But just like the waves in the water, as the waves travel, for both the water and the graded potential, they get smaller with distance. So what that means is, let's say we depolarize this spot right here. So a neurotransmitter binds right here. And we depolarize that spot right there, goes from negative 70 to negative 50. That's a depolarization, right? Which is then going to depolarize the next spot, but it might only depolarize it to negative 55, which then depolarizes the next spot to negative 50. Whoops. I made a mistake. I went the wrong way with my math. Bear with me here. Where I wrote negative 50, what should I have written? Somebody may have caught me on it. Negative 60, which then depolarizes the next spot to negative 65, and the next spot to negative 68, and the next spot, the axon hillock, to negative 69. So in this case, we see there was a depolarization of 20 millivolts at first. But then as it traveled, the depolarization became 15, 10, 5, 2, 1. And that's it. So the change got smaller with distance. Now, would this traveling depolarization, this graded potential, would it cause a signal to be ignited in the axon and then to travel all the way down the axon? Yes or no? The answer is no. Why not? Well, what value did we get to right here? Negative 69. Negative 69 is not negative 55, right? We need the axon hillock to get to negative 55 because that is our magic number. That is our threshold potential. Okay. Excellent. Excellent. Let's see. I think I am going to pause this and end this video right now, right here, because it's going to end up being like a super long one if I don't do that. So I'm going to do one more. We're going to end this one right now, and we'll do one more. So this has been great. Hopefully you guys have stayed with me. I know this is challenging here. We were not moving too fast. Although maybe it seemed like we were. Let's try not to. So I will see you on the next video. Bye-bye.